Hello students, welcome back to yet another session, and in this session we are going to see heat transfer through solar radiation, infiltration and ventilation. First we will see heat transfer or heat gain through solar radiation. As we discussed in earlier sessions, so this is the syllabus or this is the content of unit number 5, and we are going to discuss the heat transfer through. Already we have discussed through structure. Now we are going to see solar radiation and then appliances. We have infiltration and ventilation also. So heat gain, it is heat transfer as well as heat gain. Heat gain is happening actually from solar radiation. The solar radiation striking external surfaces of a building such as walls and roofs, so significantly contributes to peak air conditioning loads. So here solar radiation is one of the major source of load, air conditioning load. So this heat gain is governed by several factors such as factors influencing solar heat gain. So altitude, angle of the sun. So altitude, angle of the sun. So angle, the sun actually travels from east to west, so there will be always altitude change. And clearness of the sky. So when there is a cloudy sky, there will be lesser solar energy or solar source. And position of the surface relative to the direction of the solar rays, absorptivity of the surface. So there will be absorptivity index also, so that should be as high as low as possible. Ratio of heat transfer coefficients, so they are coefficients. Altitude, angle of the sun, so depends on local altitude, time of year and hour of day. So normally in midday there will be very high solar radiation. And types of solar radiations: direct radiation, sun's rays directly impinging on the surface. So diffuse sky radiation, so it is radiation scattered by atmospheric moistures and surface not directly exposed to sun rays. And solar heat gain coefficient is defined as the fraction of incident solar radiation admitted through a window. So here solar heat gain coefficient is defined like this, and it is the fraction of incident solar radiation admitted through a window. So here solar heat gain sensible through outside walls and roofs. So here it is sensible heat only, there is no moisture involved here. So the nature of transmission, the transmission of heat is non-steady and it is periodic, as outside air temperature and solar radiation intensity vary cyclically over 24 hours. So it varies from low to high every day in a cyclic manner. Part of the heat is stored in the wall due to its thermal mass and released later, delaying peak room temperatures, and shows the difference between external instantaneous heat gain and actual indoor load. The shaded area represents the storage effect of the wall, heat retained and released later. So this is the at a different time in a day how the temperature is rising. So the temperature is goes high around 2 p.m. and it is becoming very low at 2 p.m. Sorry, 2 10 p.m. and here the actual room inside. So inside the room temperature is following this curve, and outside the temperature curve is like this. And inside it is starting from this point and reaching at this similar point at 4 a.m. So 6 a.m. to 4 a.m. and 4 a.m. to 6 a.m. it remains lower in the entire cycle. So these are the curves of instantaneous load. and total equivalent temperature differentials for calculating heat gain through sunlight and shaded roofs. And these are the tables, and you can see the sun time at 2 p.m. Is actually very high, and you can see in all the materials it is very high at 2 p.m. So here at same the different materials. So 10 centimeter concrete or 10 centimeter concrete plus 5 centimeter insulation. So different structures establishes this radiation, and here it is the 2 p.m. is always higher. So this is the 2 p.m. You can see for all the materials the higher temperature. So at the non-latitude wall facing, so even the you can see the dark and light, and you can compare this table also. Anyhow, I am giving you this material, so please compare this for frame. It is happening like this, and for 10 centimeter brick and stone veneer frame, it is happening like this, and 20 centimeter hollow title are 20 centimeter cinder block, so it is happening like this. So this the latitudes are given northeast, east, southeast and south, and north, southwest, west, northeast, northwest, north. So for different directions and altitudes, how the difference is taking place in temperature. So 20 centimeter brick and a 30 centimeter brick, the same table continues, and 20 centimeter concrete or stone, or 15 centimeter or 20 centimeter concrete block, 100 centimeter concrete or stone. So here the radiation will be lesser. So because thicker wall here. So solar temperature, the solar temperature is a hypothetical temperature used to calculate heat received by the outer surface of a wall. So heat received by outer surface of the wall is known as solar air temperature. It is hypothetical temperature only. It is not there is no exact measure. That's why it's hypothetical measure temperature. Through the combined effects of convection and radiation from solar exposure, the heat transferred by convection is given by F naught T naught minus TOS. So QC is the heat received by convection. F naught is outside film coefficient. So that is in terms of watt per meter square Kelvin, and outside air temperature is T naught. TOS is temperature of outside surface of the wall in terms of degree Celsius, and heat transfer by radiation QR equal to I alpha. So QR equal to heat received by radiation, and the I is total radiation intensity, that is in terms of watt per meter square, and alpha is the absorptivity of the surface. And this is the outside surface and wall, and you have inside surface. So solar temperature representation shows the external heat gain through combined radiation and convection at the outer wall surface. So total heat received by outer wall surface, so that is equal to QoS. So outer surface is OS, and QC plus QR equal to F naught T naught minus TOS plus I alpha, and substituting into energy balance, and QoS equal to F naught T naught I alpha by F naught minus TOS. So that is equal to QoS equal to the heat transfer at outer surface equal to F naught TE minus T naught TOS, and where so TE equal to T naught plus I alpha by F naught, and TE is the solar temperature. So TE is the solar temperature. So solar heat gain through glass areas. So glass contributes significantly to solar heat gain in building. So glasses are a major conductors of heat from outside to inside. When exposed to different direct and diffuse radiation, the glass the reflects part, absorbs part, and transmits the rest of the interior. So to the into the interior, and it partially it reflects, it partially absorbs, and transmits the remaining into the interior. And process of heat gain: absorption heats the glass surface, and glass radiates and convects the heat to interior surfaces, that is room, exterior air or sky. Heat gain depends on glass temperature relative to outside and inside temperatures. And if the glass is hotter than outside air, no conduction occurs outward. So heat enters the room by radiation and convection. So these are the two processes, and radiation and convection. And also we have seen conduction in earlier session, and internal and external air currents also redistribute heat. So solar heat gain through glass areas, net heat gain expression is net heat gain is equal to transmitted solar radiation plus heat flow by convection and radiation between glass and interior. And if we neglect the storage heat in the glass, so heat flow by convection and radiation equal to absorbed radiation plus or minus net radiation and convection exchange with outdoor air. So a well-designed air conditioning system helps maintain dry, stable indoor air conditions despite solar exposure. And solar heat gain through glass varies by orientation, north, south, east, and west, and time of the day. Sky conditions, it may be clear or clear or cloudy. Season and latitude. Standard solar heat gain values are often supplied during exams, are available in ASHRAE tables. So solar heat gain values are often supplied during exams. So points to remember here: the solar temperature integrates radiation plus convection into a single effective temperature. So glass introduces direct plus indirect heat gain via transmittance, absorbed re-radiation, convective exchanges, and heat flow through glass is complex and influenced by solar geometry, material properties, and ventilation conditions. So heat gain due to infiltration. So infiltration air refers to the uncontrolled air that enters a conditioned space through cracks in windows and doors and openings caused by pressure differences. So this phenomena is primarily caused by wind velocity and direction, temperature and density differences between indoor and outdoor air. And estimation methods are two main methods: crack leak method when used when greater accuracy is required, crack length method, and air change method. So this is commonly used method. So formula for air change method: infiltrated air volume, that is meter cube per minute, is equal to L into W into H into AC by 60. For whole building infiltration, use half of the calculated volume, as infiltration is dominant on withdrawal side, windward side only. So where L is the room length, M is the room width, and H is the room height, and AC is the number of air charge changes per hour. So air changes per hour is AC. So number of air changes per hour, that is AC, equal to kind of room building and number of air changes per hour. So rooms with no windows or outside doors, it is AC is referred as 0.5 to 0.75. Rooms one wall exposed, so that is 1, and rooms two walls exposed, that is 1.5. Rooms three walls exposed, that is 2. Rooms four walls exposed, that is 2, and entrance halls is 2 to 3, and reception halls is 2, bathrooms is 2. So infiltrated air through doors, so per person per passage, and this is uncontrolled air. Now whenever we open door, so there will be air from one room to a confined room will enter, and usage of door, infrequent usage, so freely revolving door, so meter cube per pass it is 2.5, and the average usage is 2, and the heavy usage is 1.5, and door with brake is 2, 1.75 and 1.25 respectively. So heat gain due to ventilation. So purpose, ventilation supplies fresh outside air to remove odors, CO2, carbon dioxide, smoke and other gases. Outside air adds both sensible heat as well as latent heat. So via temperature and via humidity. And now the guidelines are as follows. Minimum half air change per hour is recommended in building with normal ceiling heights. And in infiltration air volume, required ventilation increases ventilation volume to match the confined temperature, and proper air conditioning design considers both ventilation and infiltration loads. So outside air required per person. So this is the table you can see here. Apartment. So here the application is application and smoke recommended in meter cube per minute per person, and the minimum values are given here. And these are all the applications: apartment, banking space, barber shops, beauty parlor, cocktail bars, departmental stores, drug stores, factories, funeral parlors, hospitals, private rooms, hospitals, wards, and hotel rooms, meeting rooms, offices, general offices, private restaurants, cafeterias, theaters, and smoking here. In most of the cases, it is none, and recommended meter cube per minute per second, the values are given here, and the minimum values are given here. So this is minimum value is also meter cube per minute per person. So this topic we are concluding here, and in next topic we will see the appliances, and appliances are mostly the electrical appliances only. So for this topic you can refer the RS Kurmi book or CP Aurora book, but I prefer you to recommend you to refer RS Kurmi rather than Aurora, CP Aurora. So we stop here, students. Again, we will meet in next session where we are going to complete the second topic, appliances. So last segment in this topic is appliances, home appliances or electrical appliances, that we will discuss in next session. Thank you, students. We stop here.